Welcome to the presentation on DiConStruct, causal concept-based explanations through black box model distillation. This work is published in the proceedings of the Conference on Causal Learning and Reasoning. Let's start by outlining the motivations of this work. Machine learning methods are increasingly used to make high-stake decisions, for example, in areas such as medicine, criminal justice, and fraud detection. The field of explainability looks into approaches that make the machine learning model decisions more transparent. The aim of such explainability methods is to make a human understand why a model provided a certain output. The most common class of explainability methods can be grouped into feature-based methods. These methods provide a score per feature, reflecting that feature's contribution to the model output. However, feature-based explanations are often difficult to interpret. This is especially true when there are many features or when the meaning of those features are not obvious to humans. One solution is to provide explanations in terms of human understandable concepts instead of features. For example, concept bottleneck models are neural networks where one intermediate layer, the bottleneck layer, has each neuron representing a single concept. In this toy example, 5 concepts related to health indicators are shown in the bottleneck layer, and the network will try to predict the likelihood of cardiac arrest from those. Such concept bottleneck models are trained using 2 objectives, namely, learning to map the inputs to the corresponding concepts in the bottleneck layer, and learning the main task. In this toy example, it is predicting the likelihood of cardiac arrest. Learning with these 2 objectives simultaneously often leads to a trade-off between the main task and the concept prediction task. So to briefly summarize the limitations of current explainability methods, first, feature-based explanations are often difficult to interpret. Using concept-based explanations improves on this, but leads to trade-offs between the main task and the task of mapping the inputs to the concepts. Finally, a point that we haven't discussed so far is that none of the above methods allow for counterfactual reasoning, meaning that they don't allow us to reason about alternative outcomes. Ideally, the explanations would come in the form of a structural causal model, or SCM. An SCM represents the causal relations between variables through a directed acyclic graph and mathematical equations describing how each variable is influenced by the other variables. In this toy example, a fictitious SCM is shown using the same concepts from the concept bottleneck example earlier. Here, the nodes represent the concepts, with darker colors denoting higher likelihood of the respective concept being present, and the edges represent the direct causal relationships, where red represents a negative influence and blue a positive influence. We can see, for example, that this person is not a smoker, which has a slight positive influence on the weight and a negative influence on cholesterol. Given such an explanation, one can now perform counterfactual reasoning because all causal interactions are properly modeled. For example, one could ask, what if this person would stop drinking? This intervention in the SCM would result in a new likelihood for cardiac arrest, taking the interactions of drinking to the other concepts into account. A concept bottleneck model would ignore any interaction between the concepts, therefore not providing a rigorous way to perform counterfactual reasoning. Now that we have motivated our work, let us dive into how we actually provided solutions to the limitations of current explainability methods. We propose the following goals for the limitations that we discussed earlier. Firstly, to use concept-based explanations that are more interpretable than feature-based. Secondly, to use post hoc explanations without interfering with the machine learning model itself. And thirdly, to incorporate causal principles in the explainer. Let's now dive into how we translated those goals in our proposed method. First, Let's look at the required inputs. We need an input instance X, as well as a directed acyclic graph or DAG, containing the concepts as nodes, and finally, a black box classifier that we want to explain. A few important assumptions that we make here are that the concepts and the DAG are known a priori. This means that for now, we assume the data comes already labeled with the concepts and that the DAG is given either by experts or learned using causal discovery methods. We also assume that the set of concepts are complete, or in other words, that we do not need other information to accurately predict the output. Next, let's look at what we call the exogenous model, the part of our solution that generates the external inputs to the causal model. Since we have a node corresponding to each concept in the causal model, the task of the exogenous model is to generate one variable per concept. To achieve this, a feed-forward neural network maps the input X using a number of common blocks followed by a number of concept-specific blocks to an output per concept. These outputs represent the exogenous variables, and as already mentioned, we will have one per concept. Once we map the inputs to the exogenous variables, the structural causal model is constructed using the following equations. Firstly, the concept likelihoods, which are represented by the nodes, are computed using a bias term B, the logit of the corresponding exogenous variable U, and the sum of contributions from the parent nodes M, and these contributions are the causal edges pointing to the respective concept. These contributions can be computed in two ways, either generating global explanations, meaning that one wishes to find the most important concepts on the level of a whole dataset, or local explanations if one wishes to find the most important concepts for the prediction of a single instance. In the global case, the edge contributions are computed using the logit of the source node likelihood multiplied by a global learnable weight. In the local case, the weight itself is dependent on the exogenous variables associated to the input through a learnable mapping. The computation then proceeds all the way from the nodes that have no parents to the leaf node of the graph, which is the node mimicking the black box model score. The explainer is then trained end-to-end, as is typical for deep learning, and combines three objectives. The first objective is the exogenous independence loss, stimulating the exogenous variables to be independent. This is an assumption of causal models, because if there would be a dependence between exogenous variables, it would imply some common cause that is not taken into account. The loss is constructed by using a discriminator that tries to distinguish between a batch of instances and that same batch, but randomly shuffled over the columns for that input, breaking any correlation between the exogenous variables. If the discriminator performance becomes random, it means that the exogenous variables are independent because the joint distribution is indistinguishable from the product of marginals. The second loss is a cross-entropy loss for the concept prediction task, and the third is the cross-entropy for the main classification task. The three objectives are combined using two hyperparameters gamma and beta, which determine the strength of the exogenous independence and concept losses compared to the main classification loss. Finally, given the fully trained explainer, one can compute the concept attributions, or in other words, the importance of a certain concept in causing the output score as follows. Given an input instance, we make two interventions. Either we turn the concept fully on or off. And in both cases, we compute the absolute difference in output score with the original score. Summing both absolute differences results in the concept attribution. Now that we have explained how our method works, let us dive into the experimental setup. We use two datasets to test our method. Firstly, the publicly available cub bird classification dataset, which is already annotated with concepts. Secondly, an in-house merchant fraud detection dataset, where data was partially annotated with concept labels by our fraud analysts, and the remaining part is labeled by a separate model trained on those analyst labels. We evaluated the method using three metrics, namely the main task performance using the true positive rate at a 5% false positive rate, the fidelity of the explainer in mimicking the black box model scores by using 1 minus the mean absolute error, and the concept performance using the average accuracy over concepts. We also use various baselines, namely the concept bottleneck model, the black box model performance on the main task, which we denote as task baseline, and the model trained to only predict the concept labels, which we denote the concept baseline. Finally, the DAGs are obtained using three causal discovery methods, and the best performing method was chosen as part of the hyperparameter optimization. Now, let us look at the summary of the results of our experiments. In this table, we provide the results on the cub dataset on the top and the merchant fraud dataset below. Firstly, we can observe that the performance on the main classification task of our method is better than a concept bottleneck model, because our method does not interfere with the black box model denoted here as the task baseline on the third row. The concept bottleneck model performance is worse because it is jointly trained on two objectives, which are the main task and the concept prediction task. Secondly, observe that the performance on the concept task is on par between our method, the CBM, and the concept baseline. Finally, we can observe that the fidelity of our method is close to perfect, denoting that our explainer is closely mimicking the black box model scores. Let's look at an example explanation from our merchant fraud dataset. In this case, a transaction is deemed to be highly likely fraudulent, as can be seen from the black color of the fraud node. Given the graph on the left, we can see that suspicious device, suspicious delivery, and suspicious email are concepts that are likely present. We can also see that good customer history is less likely, and that this in turn gives a positive contribution to downstream concepts related to fraud, which would make sense in this case. On the right, we can see the concept attributions computed from this structural causal model. Here, we can see that the concept with the highest contribution is suspicious device. Finally, one could perform counterfactual reasoning on this type of explanations, for example, by intervening on the suspicious device node, by setting it to a low value if the analyst deems that this device is not as suspicious. And in turn, one could observe how this would affect the output score. This was a summary of results, but we referred to the paper for a more comprehensive overview of all the experiments that were performed. Now, let's conclude the presentation with a few takeaways. In this work, we proposed an explainability method that is concept-based and causal, and since it is a surrogate model, it does not affect the predictive performance of a black box model. By operating on the concept level, our method provides interpretable explanations, and by incorporating causal principles, our method allows to perform reasoning. Thank you very much.